Hello, welcome back to ECE484, Fall 2021. Hope the first week back since reading week is going okay for everyone. Let's get started. So we are doing chapter 5, which is about nonlinear systems. The idea being that, the real world is generally nonlinear, right? These linear models that we've been studying for the first part of the course, they don't occur naturally that frequently. Usually the systems we want to control are naturally nonlinear. And so we're trying to talk about a few strategies to deal with these nonlinear systems and how to control them. Okay, simple strategies, because it's a big topic. And the first strategy we've been talking about, or what we were talking about last class, was this notion of linearization, right? So we're going to approximate a nonlinear model using a linear model, okay? And we're using state space models to do this because, one, nonlinear systems are easy to express in this standard form, in this nonlinear state space model form. And the second thing is it gives us a nice systematic procedure for doing this approximation, for doing the linearization, okay? And so we went through that procedure last time, and let's kind of remind ourselves what it's all about. First thing you have to do is you have to figure out where you want to approximate this nonlinear system. And that, we talked about this notion of an equilibrium configuration of a nonlinear system, okay? And so roughly speaking, it's a place where the system is stationary, right? It's a value of the state and a value of the control input that if we were to initialize the system there, then in theory, the system should stay there for all future time, right? It's kind of an equilibrium. It's perfectly balanced in some sense, okay? Mathematically, it's a pair, x bar, u bar, so a value of the state vector, a value of the control vector, such that all the derivatives vanish, right? So the right-hand side of this differential equation equals 0. Okay, once you've got your equilibrium configuration, then you go about doing linearization. And we justified the procedure last class, but at the end of the day, when you get down to brass tacks, it's a matter of taking some partial derivatives. Okay, so you start with your nonlinear system. You linearize to get this linear model, and we'll go through the various quantities in this linear model. So first, let's talk about the matrices. The matrices A, B, C, and D. So A is just a matrix of partial derivatives of the nonlinear model with respect to x. So you take the nonlinear state equation, take partial derivatives of this function with respect to x, that gives you the A matrix. Don't forget to evaluate it at the equilibrium configuration. B, which tells you how inputs affect the state, is essentially you take the state, it's over here, and what do? You take the state equation, and because we're looking at the way inputs affect the state, we're going to take the partial derivatives with respect to the input vector, okay? If you have a single input system, B is just going to be a single column. If you have a multi-input system, B will have multiple columns. Okay? And then you do the same thing to get this linearized output equation, to get the matrices C and D. It's the exact same idea, except, of course, we're going to use the output equation to do it instead of the state equation. Okay? But otherwise, it's the same idea. Okay, so fine. There's these other symbols, these deltas. Let's talk about that for a second. This linear approximation is going to be good in the sense that the linear model will behave similarly to the original nonlinear model as long as these two quantities, delta x and delta u, are sufficiently small. And so what are delta x and delta u? The intuition there is that they're sort of a measure of how far the nonlinear system's state is from equilibrium, as well as how far the control signal is from its equilibrium value, okay? And then the question of how small do they have to be? I mean, certainly there's some theory that you could apply there, but I would say that in practice, it's best addressed through simulation, right? You design your controller for the linear model, you go and test it on the nonlinear system, and if it works well, you're happy. If not, maybe you're going too far away from your equilibrium configuration, and your model is becoming poor. Okay. So we took this and we turned it into a procedure essentially for doing linearization, and then we started doing it on an example. So I'm going to continue that example today. So this is literally what we had written last class, so I'm just going to remind you of what we were doing. We wanted to linearize the pendulum, this physical pendulum over here, at the upright position. Right, so think of it as a crude model of like a Segway or something. Um, so our procedure was first find the equilibrium configuration. So that's what we did in step one, right? We knew that we wanted the output, the position of this system to be equal to pi. That gave us this constraint here, which really, I should rewrite this. I should rewrite this in this way. Because the output is just equal to x1. Okay, so we had to solve this equation. Notice all I've done is I've set on the right-hand side, I have f of x comma u, where I've replaced the x with x bar and u with u bar. I've set the derivatives to 0, and I solve. And this last constraint, again, as I mentioned last class, it's sort of application dependent. And in this case, the application is we want to linearize at the upright position. Okay, solving, we found this value, right? So the state at equilibrium is pi 0, so position is upright, velocity is 0, and we aren't applying any torque. Then we went to compute the Jacobians. So again, here's the nonlinear model over here. This is the state equation that tells me the function f. This is the output equation. It tells me the function h. And then we went through the various calculations to get our matrices A, B, C, D. Okay. So this was a specific example of what we were doing, of what we talked about just a moment ago. And so the last step was to write down the linearized model. So let's do that. Let's write down the linearized model and then move on to the next topic. So once we've computed A, B, C, D as above, we now have our linearized model. Okay. And this step really is just, it's the output of the procedure. You've already got all the ingredients. We're just going to write it down, kind of put them all together. So our linear state space model that we get looks like this. Okay, and I'm just going to fill in the various, I'm going to rewrite basically those matrices from above. There's A, so A will be this thing, B will be this thing, C is here, and D is 0, so I didn't even bother writing it. So if I fill in the information, we get 0, 1. Oops. So there's our A matrix. Our B matrix was this thing. And our C matrix was this. Okay, so that's it's a linear state space model. Remember we said that the linear state space model has this particular form with matrices. So the equations have a linear form. So again, what are the quantities delta x and delta y? Well, delta x in this case is the state minus the equilibrium, which for the pendulum, the state is the position and the velocity minus the equilibrium point associated with the upright position, right? So delta x is a measure of how far the pendulum is from being upright and stationary. Similarly, delta u in this case happens to equal just u of t, right? So because at the upright position, there's no applied torque at the equilibrium, right? We did this other example last class where the pendulum was sideways. There we had to apply a torque, and so in that case, delta u would not just equal u, right? It would be u minus that torque you need to balance gravity. Okay, and delta y's similarly. So y bar here is the value of the output at the equilibrium configuration, which in this case is just pi. Okay, So linearization. So now we have a way of going from a nonlinear model, which tend to arise through physics, and naturally their systems will be nonlinear, and we have kind of a systematic method to approximate them at an equilibrium configuration. All right, so our objective, of course, is to then design controllers for the linearized model so that we can hopefully control the original nonlinear system, right? That's the objective here. We want to use our nice, simple linear tools to control nonlinear systems. There is one small issue here, is that when we design our controllers, up till now, we've used a transfer function model of our plant. Okay, so we have one little step we need to do if we want to apply, for example, the tools of Chapter 3. We need to take this linear state space model and turn it into a transfer function model so that you can do the usual types of control designs that you've done up till now. Okay, so let's talk about that. So this is obtaining a transfer function model from a state space model. Again, the output of our linearization procedure is a linear state space model. We would like a transfer function, so we could do, frequency domain design, draw Bode plots, do pole placement like we did in Chapter 3. Okay, so we want a transfer function. Okay, so we start with a state space model. Okay, I've dropped the deltas here. It is true that in most cases, in most real systems, this linear state space model will come from linearizing a nonlinear system. But it's common that we would say, we understand that this linear system comes from an approximation, and we're just going to drop the deltas. Okay, and so I've done that here. But if you want to keep the deltas, you can keep them there. It doesn't matter. It's just we're starting with a linear state space model. Could come from naturally being linear, or it could come from linearization process. Okay, this is all we're going to do essentially here is take Laplace transforms. Laplace transforms plus some algebra, and we're going to get our transfer function. So let's take Laplace transforms. And because we're interested in transfer function models, we're going to assume all the initial conditions are 0. Okay, and so you may remember that time derivatives turn into multiplication by s in the Laplace domain. So that x dot vector is going to turn into s times the vector of Laplace transforms of x. So I'm going to write that here. Oops. That's on the left-hand side, and I'll explain a little bit more about that notation in a second. On the right-hand side, you may remember that the Laplace transform is a linear operation, right? If I take the Laplace transform of the sum of two signals, it's the same as taking the Laplace transform of the first signal plus the Laplace transform of the second signal. Okay, so I'm going to use that linearity here to pull the A matrix out of the Laplace transform operation. And get this equation. Okay, I do the same thing with the output equation. Okay, so here, I do want to point out that x of s because remember, our state vector could be large. Remember, think of the quadrotor example. There we had 12 states. So x of s here is that Laplace transform of 12 different states. So x1 of s, in general, we said n was the symbol we were going to use. So that's a vector. Okay, and same with u and y. In general. Let's see if I can squeeze this in here. I think I can. y1 of s to yp of s. Hopefully you can see that's a p at the bottom. Okay, so hopefully you can see that. So there's n states, m inputs, p outputs, the same notation we've used throughout this chapter. Okay, so that's the only thing here. It's a Laplace transform, a vector of Laplace transforms. Okay, now the basic idea is I have this x showing up in the output equation, the state. I don't like that. I want a transfer function. A transfer function directly relates u to y, right? It takes inputs to outputs with no intermediate states. So I want to eliminate x. So the rest is just algebra to get rid of x in the output equation. Okay, so I don't like x of s. I don't want any states in my transfer function model. So what I'll do is I'll use the top equation there to get an expression for x, and then I'll plug it into the second equation. So from the top equation, we have bringing ax over to the left, and keeping in mind that these are vectors, these are not scalars, right? So remember, I is the identity matrix. This was a notation way back, I think first week of lectures. I is a matrix with ones along the diagonal, zeros everywhere else. Okay, so I brought ax over to the left, and now, I'd like to divide both sides by si minus a, but of course I can't do that. That's a matrix, that wouldn't make sense. So what I can do though is multiply both sides by the inverse of that matrix. And so I'll do that. Okay, that is not division. Okay, that is not division. Formally, it looks like division. Notation kind of is evocative of division, but it is not, right? I'm multiplying both sides of the top equation by the inverse of that matrix. Okay, and now finally just plug that expression for x into y of s. And there we go. That's our transfer function in terms of the four tuple a, b, c, d. So let's okay. Now, for multi-input systems, you might hear the term transfer matrix, right? Because it's a matrix of transfer functions. But for a single input, single output system, this would just be a scalar transfer function, the ones we've seen many times. Yeah. So so this is a way to go from a state space model. Remember, a state space model is A, B, C, D, to a transfer function model. I'll mention here that MATLAB has a function which can do this. Called SS to TF. Okay, so it'll take the matrices A, B, C, D, and it will produce the transfer function associated with those matrices. Okay, so let's do an example of this calculation, just so it's really straightforward actually. So let's do an example. This one is not from the notes, this example. So remember when we started this chapter, when we first introduced state space models, we had this cart with an applied force and drag, right? And the drag was possibly nonlinear, and that we kind of used that to motivate this notion of a nonlinear model. We made a remark after that example where we said if the drag was linear, we could get a transfer function, right? So I want to go back and revisit that remark and say we had a state space model in that example. We also had a transfer function. What's the relationship? Well, we just discussed the relationship, so let's see that it's consistent with what we saw earlier. So recall the cart from example 511 with linear drag. And so the model there was simply this. Right, so I had a mass, d was the coefficient of drag there, and it was linear. In that example, we found a state space model for this system, and so let's recall what it was. As usual with our mechanical systems, we took position and velocity as our states, and we had the following. Okay, that was the state space model. And the output equation, the output was the position of the cart, so it was just the first state. Okay, so let's do this calculation to find the transfer function, right? So of course, as we said in that remark, I could take the simple equation here, and I could find the transfer function, but let's do this calculation up here and verify that we get the same thing that we would get otherwise, all right? So let's do that. The associated transfer function model is, well, we just go through the calculation carefully. Okay, so I'm just writing down the equation that we derived above. In this case, there is no D matrix, so notice that D doesn't show up, right? Otherwise, I'd have a plus D showing up here, but there is no D matrix, so let's leave it at that. Okay, so C comes from the output equation. So in this case, C is 1, 0. A is that 2 by 2 matrix there. Okay, but I need to do S times the identity matrix minus that matrix above. Okay, so when you do that, you get the following. Okay, so that's SI minus A. I haven't taken the inverse yet. I'm keeping the inverse sign there. And then finally the B matrix. Is there. Okay, so when I want to take an inverse of a matrix, it's nice to use Kramer's rule to do that. So I'm going to remind you here, a little aside. For these types of calculations, when I want to compute by hand this expression, it's useful to use Kramer's rule for solving linear equations, and that you get this formula, which you may remember from linear algebra. Okay, so the numerator is the adjoint or adjugate. Those are a couple of classical adjoint, adjugate. This is an n by n matrix. And if you remember, the determinant of a matrix is essentially a polynomial in S, right? So this is going to be a polynomial. Okay, and I'm going to use that way of taking the inverse of a matrix to compute the inverse of that 2 by 2. Now, a 2 by 2 matrix is so simple to invert that we can just very simply do it by hand. But let's go through the calculation. So I'll do leave space for the inverse here, just to kind of walk you through it, to remind you how it's done. Okay, so the determinant of this matrix, of a 2 by 2 matrix, is going to be the product of the diagonal elements minus the product of the anti-diagonal elements. Right? And that's going to be our polynomial that we get at the bottom here. So let me write that polynomial. So this will be our adjoint here. But the polynomial we get, so again, multiplying the diagonal elements, I get s squared plus s times d over m minus 0. So in this case, 0. So I'm just going to write that here. S S plus D over M. There's my determinant. And for the adjoint of a 2 by 2 matrix, it's really simple, right? Switch the diagonal elements and change the sign on the antidiagonal elements. So swap the diagonal elements in the 2 by 2 and then change the sign of the other ones. All right. And you can look up how to do it for higher or bigger matrices, right? Like, so you've certainly seen this before. Okay, the rest is just doing this calculation. Now, by the way, in this case, it's a 2 by 2. It's very simple. But if this had been a bigger matrix, and I had to do this by hand, you can be smart about it, right? Look ahead, right? So this C matrix here is only going to pull out the first row of this inverse. This B matrix here is only going to pull out the second column. So first row, second column, this is the only term that matters in this inverse. All the other terms don't matter. So if you see that pattern, use it to your advantage, right? Maybe you don't need to compute the entire inverse. Just compute the components you actually need. All right, and the rest is just multiplying out matrices. And so you will get which is exactly what we would have gotten if we'd just taken the Laplace transform of the original equation. Okay. So why do we do it this way? Why didn't I just do it this way? Well, okay, we were two reasons why in this example I didn't. One, I wanted to illustrate the calculations. And two, when you do linearization, what you're not going to get an equation like this, generally speaking. You're going to get a state space model. And so you want to go from state space to transfer function. Okay. Let's do one more example. We just computed the linearization of the pendulum, so let's find the associated transfer function. Okay. So recall the model of the linearized pendulum. At its upright position. Right, this is the example that we started off this lecture looking at. Okay, and so I'll write it here for you. Okay, so we wrote that down earlier, so I just quickly write it down. So remember, delta x is measuring how far the pendulum is from the upright position. Delta u is how far u is from its the upright torque, which is 0. And delta y is the measurement of how far the output is from being upright. Okay, so transfer function. We have a, b, c, d. D is 0 in this case, so let's find it. So its transfer function is we derive this formula above, the general formula. D is 0 for the system. Plug in the information for our particular system. So C is 1, 0. SI minus A. Inverse. Okay, so I just plugged in A, B, C to the equation. D is 0, so this doesn't show up. Same idea, I'm going to do this adjoint over determinant thing. So we get that this equals. So let me write it this way. That'll be my determinant, the denominator, and the numerator will be what's left. So the determinant of that 2 by 2, again, multiply the diagonal elements, subtract the anti-diagonal elements, and we get s squared minus (1.5) g over L. Okay, so there's the denominator. And in the numerator, okay, let's go through the gory details. Adjoint of a 2 by 2 is simple. Swap the diagonal elements. Change the sign of the anti-diagonal elements. Multiply it out. Okay. And so now we have this transfer function. Notice that, remember, this is the transfer function describing the linearization of the pendulum at its upright position. So notice, it's unstable. We have a pole with positive real part. Of course, this is what we would expect, right? We would expect that this pendulum is not stable upright. If we don't apply feedback or some sort of control, this pendulum will not stay upright. And of course, that's evidenced in the instability of its transfer function, right? On its own, it is not stable. So we make the observation. This is open loop unstable. As you'd expect. Okay. Pendulum will not stay upright on its own. You're going to have to do something, right? And that's where feedback will come in. Okay, so let's step back to think about what we've done so far. You have a nonlinear system because the physics are naturally nonlinear, or life is complicated, so things will typically tend to be nonlinear. We put it into state space form. That's the first thing we did. Then we learned how to linearize it to get a linear state space model. And now we just learned how to take that state space model and generate a transfer function. The last thing to do is, now that you have this transfer function, let's do control design, right? We're back to where we were in chapter 3 in some sense. And so let's see if there is any sort of quirks that happen when you try to do this for a nonlinear system. So the idea would be you get this transfer function, design the controller for the transfer function, the plant, and then you control the original nonlinear system. So let's see how this works. So 522, control design using linearization. Okay, and so the basic idea is the following. Linearize a nonlinear system. Design a controller for the linearized model. Finally, use the linear controller to control the original nonlinear plant. Okay, and so let's see how this works. The best way to do it is through an example. So So we will do an example from the notes. Okay, so it's going to be a mechanical system. It's sort of a cart, but the cart is going to have this nonlinear force acting on it. It's going to be what we're going to call a softening spring. So here's the setup. It's a very bad square. See if I can do better. Nope. There we go. Okay, so there's our cart. It's going to have mass m. Right? There's going to be a spring connected there, and there will be friction on the floor, but we're going to model that as a damper. Okay, and then yeah. So let's label a few of these things. So the damper, let's assume, in the position of the cart, we'll call it Q. Right, so the cart has position Q. There'll be an input to the system, which will be an applied force. So let's take this input here. Okay. The damper, let's just assume that it's linear damping, so it has coefficient B. But our spring is going to be nonlinear. So I'm going to write this as, instead of just writing a constant, I'm going to say that it's the force exerted by the spring, or force of the spring, is not just K times Q, it's K of Q, right? It's a possibly nonlinear function. I'm going to write down that function in a second. But that's the idea. We have a nonlinear system, and the source of the nonlinearity here is the spring. Okay? And so we apply Newton's equations. We get mass times acceleration is equal to the sum of the applied forces. Okay? And K of Q, for us, is going to be a so-called softening spring. Okay, and so what does the softening spring do? Basically, as you stretch out the spring more and more, it starts to exert less force, right? So at first it's kind of like a linear spring, but eventually if you pull it too far, it stops behaving like a linear spring, right? So you can think of it as like the coils are getting kind of stretched out. Okay, so this is a softening spring. Right, it softens as you stretch it, and the model is valid as long as AQ is less than 1. And K is just a constant. Okay, so the nonlinearity is that the spring has this kind of linear regime where it's kind of like when Q is small, it's like a linear spring, but as Q gets larger, it kind of becomes nonlinear. Okay, what do we want to do? We want to design a controller to keep the cart at the location Q bar equals 0.5. Okay, so we want to keep the cart at a particular location, but we also want to do step tracking. What does that mean for us for step tracking? We're going to keep it at 0.5, and then we're going to command it to kind of deviate from 0.5, right? So from 0.5, go a little bit to the left, or I guess right, or go to the left. Okay, side to side. So keep the cart at location Q equals to 0.5, and track step references. Okay, so we could try to design a nonlinear controller to do this, but the bread and butter of industrial control is linear control. And so we're going to linearize, design a controller for the linearization, and then test on the nonlinear system. Okay, so let's go through our procedure. We need to get a linear model. So state space model, linearize, transfer function. So step 1, state space model. So what do we have to do? We have to pick states, inputs, outputs. So mechanical system, remember our rule of thumb, positions and velocities. U, of course, is the applied force. And given that we're interested in controlling the position of this system, it's natural to take the output to be the position. Okay. So with those choices now, we just have to go up here to our model and rewrite this in terms of x's, u's, and y's. Okay, so that's nothing special going on there. That's just a rewriting of that equation. So we get that x1 dot equals x2, and x2 dot equals. So I'm just literally rewriting the equation that we had above. Okay, so remember, x2 dot is q double dot, and q double dot comes from the equation above. And the output is the position. Okay, so there's our state space model. Now, we want the cart, we want to control the cart near the position q equal to 0.5. So that's a natural kind of, again, the application tells you what the equilibrium should be. And so in this case, we're going to look for an equilibrium configuration where the position of the cart is 0.5. So we're going to find a linear approximation, or a linear model, to approximate this system. Near q equal to 0.5. Okay. So what do? We solve for the equilibrium. So set all the derivatives to 0 and solve for x bar, u bar. So that's what I'm going to do. Let me factor out that 1 over m term. And remember that the desired output is 0.5. So okay, so solve this equation to get the equilibrium configuration. And so for this case, it's actually quite easy. We will get so the position has to be 0.5, the velocity has to be 0 because we want to stay still, and then the control just has to apply enough force to balance out the force of the spring, right? So we're going to get that u is simply equal to k at 0.5. Okay? It's just balancing out the effect of the spring. So if you want numerical values, it turns out that k, if you plug it into the equation we had before, it's simply this. Okay. But you get the idea, right? We're just solving that for the equilibrium configuration. Okay. Once we have the equilibrium configuration, what do? Well, we saw it at the start of this class. We compute Jacobians. I need those 4 matrices, A, B, C, D. I mean, I won't go through so much detail. We've already done an example like that. But remember, A comes from taking the partial derivatives with respect to x of this guy and then evaluating at the equilibrium configuration. So I'm going to do that. And you can verify that you get the following. 0, oops. Let me write it down, then we can talk about it. So what happens, of course, is that we get the derivative of the spring force, K prime, evaluated at the equilibrium configuration. And so in this case, K prime of x1, I just mean dk dx1. And in this case, that equals K. Okay. So there's our A matrix, B matrix, C matrix, and D matrix. Actually, B, C, D, it's already linear, right? So when you compute those Jacobians, nothing changes. It's really the source of the nonlinearity here is the spring. So A is the only one that gets, like A, the nonlinearity gets, I guess, approximated only in A. Okay, so now we have our linearized model. Okay, so this approximates our cart near the position 0.5. And so, as always, delta x is measuring how far we are from being at that location. Delta u is u minus the equilibrium control. Remember, the equilibrium control had to balance out the force of that spring. So K 0.5. And delta y. It's just y minus the output at the equilibrium. Okay. Almost there. We're almost ready to do control design. Last thing I want to do is I want to take A, B, C, D, and I want to get a transfer function model. Right? That's what we design controllers for. Right, so let's take delta y to be the Laplace transfer of little delta y. Capital delta u to be the Laplace transform of little delta u. And so we get okay, I won't go, oh, that's just delta u, correct? Sorry, I'm not sure. This term here is hard to read. Let me see. These are all just delta, like the symbol delta with u beside it. There's no brackets. I don't know if that's the question exactly. Like everywhere, the only symbol I've used here with delta is like delta u. Delta. We use a different color. Okay. Okay, well, I'm not going to be able to finish, but you should verify that you do this calculation and you get the transfer function. You get the following. So you should verify that. I'm going to stop there. This is now this is going to serve as our plant model. Okay, and we're going to do our control design for that plant model. Now, we'll do that next time. One comment here. Of course, we could design controllers in the time domain for state space models. We will do that in this course, but we're going to do it for discrete time systems, right? So if you wanted to do that for a continuous time system, there's a course in the winter, ECE484, which deals with designing controllers directly for this system. But for us, for now, we're going to take this model, turn it into our transfer function, and we'll do regular design next class, or next week, I guess. Okay. I will see you next week. Have a good weekend, and I'll stick around a couple of minutes if there's any questions.